stage, we have Ruud. And Ruud is actually going to present the badge from last time, from MCH. And MCH, there was actually an ESP32 in it, dual core, but also an FPGA. And Ruud did something with the FPGA to do some graphics with it. He will explain everything about it. And Ruud, I will ask a really big applause to get him started. Thank you very much.
All right. Thanks everyone. Thanks everyone for coming. Yeah. Are we going? Yes, we're going. Hacker camps, they're great. They're wonderful. The best thing about hacker camps, well, besides the amazing atmosphere, great talks, using more bandwidth, and of course a chance to meet your heroes. Another great thing is the amazing badges that we get. These aren't just little name tags, these are full-on development platforms. And last time at MCH we had another beauty. We had a powerful dual-core ESP32. We had a flexible Lattice FPGA and a big slab of LCD on it. It's really, really great hardware. So when I saw that, my thought immediately went to, can I make it run 3D graphics? Well, you might be familiar with the GPU that you have in your laptop or desktop or even your phone these days. And what they do is they take your 3D objects that you've collected, some 2D texture data, lighting data, and a lot more besides. You push all of it into the GPU. GPU works for a little bit, and you get a beautiful picture.
Fix.
Yeah, is this better? So you get a beautiful. Unfortunately, the badge is not quite that powerful. So let's go back to the hardware. We have an ESP32 that's connected to the FPGA, and that is connected to the LCD screen. And how I'm going to divide it is I'm going to let the ESP32 handle all of the 3D calculations, assembling the scene and producing triangles. Those triangles will be sent to the FPGA, and the FPGA will turn them into pixels to put on the screen. And in this talk, I'm going to focus on what the FPGAs will be doing. So what do we know? What's the information that we get when we talk about triangles? What we actually get is the corners of the triangle, the vertices, and we have some information about each of them. So we have their coordinates, of course, but we also have some properties like the color of each of the corners. And with that information, we can determine what the edges between the vertices look like. So in this case, we've got two different colors and two different positions. So it will move from one position to the other position, and it will produce a gradient from one color to the other color. And with a little bit of calculation, we can calculate these gradients. So how much does the position change as you move in the vertical direction? And also how much does the color change as you move over the vertical direction? And of course, we can do that for all of the edges that we have. That's great. With that information, we can compute what would have been points along the edges for every point along these edges. Of course, we want more than just the edges. We want to fill the triangle. So we can draw between any of these points as well. And we use a similar calculation. So we look at the difference in color, divide that by the difference in the horizontal direction, and we get a gradient for that as well. But you might be seeing a problem. If we do that for every single component, that's quite a lot of calculation. And we have to do that for every line that fills our triangle. That's a lot of calculations. I want to hammer this point home a bit. Maybe you're familiar with the MR project. It's an FPGA-based system that replicates arcade systems like Pac-Man or home consoles like the Super Nintendo. It's powered also by an FPGA, and in this case, an Intel Cyclone 5. Our FPGA on the Badge is a little bit smaller, about 20 times smaller. To put it even more in perspective, a single 16-bit divider that produces a 16-bit by 16-bit division every cycle occupies 40% of the FPGA's real estate all by itself. So that's rule number 1, no divisions. But we can be a little bit smarter about how we do these calculations. So remember that a triangle in 3D is always a flat surface. It can be angled, of course, but it will always be a flat plane in 3D. Which means that if you look at any point, there will always be a constant gradient along that. That's in the z-axis, in the depth. But that's true for any property that you would have mapped on the vertices, like the red, green, and blue colors. What this means is that we really only need to calculate this gradient, the horizontal gradient, once for every triangle. So what I do is I take the widest point of the triangle, basically, compute an additional vertex along the tallest line, V4, and then I can compute the gradients as before for the color horizontally. Once we have that, we can take whatever point we have along an edge, and this gradient will always be the same. So we can always use that to do our horizontal interpolation. So this gradient always the same. And in fact, we don't even need the color gradients of the other two edges anymore, because we've already defined. So this is how we're going to divide our work then. So the ESP32 is going to do a lot of these calculations, is going to compute all of these gradients once for every triangle, and it will send that to the FPGA. And once we have these gradients, we're going to step vertically, we're going to step horizontally, and that means the only thing the FPGA really has to do is a whole lot of additions. And that's what it's going to do. So what does our FPGA architecture look like at this point? Of course, we're starting getting information from the ESP32. It's coming in via SPI. So we have an SPI controller, and the triangle data is coming in there. So whatever the ESP32 has calculated. Then there's a component that I've called calc line that moves along along the edges. And then it will pass that information, the beginning and end of a span, that the draw line component will fill in. And that will then draw the pixels to a buffer. The buffer will be displayed to the LCD screen. So the LCD screen is great. We can render triangles to it. That's wonderful. Screen 320 by 240. That sounds really, really small when we have 4K and 8K screens these days. But that's at 16-bit per pixel, which is also really, really little if we have HDR screens. That's 1.2 megabit. For the FPGA, that's actually quite a lot. More importantly, we also need a lot of bandwidth for that. If we want to produce 60 frames per second, we'll need that amount of data at 60 times per second, twice, once for writing and once for reading. And that's the minimum. Let's look at the memory that's available to us. We have block RAM. Block RAM are little pieces of memory that are embedded inside of the FPGA. They're really flexible. You can use them all over the place, but they're not very big. So in total, for the full FPGA, it's 120 kilobit. That's nowhere near what we need. The advantage of these things is that they're super fast. They can go as fast as whatever clock speed that you've configured, so they have essentially infinite bandwidth. The FPGA that's in this system, the ICE40 from Lattice, also has bigger blocks of RAM. It's got 4 what I call single port RAMs, and they total up to a full megabit, which is unfortunately just too small to fit our full frame in, but it's also really, really fast. And then on the badge itself, we have, outside of the FPGA, we also have a little RAM chip. Really, really big, spacious, more than big enough to fit as many screens as we want, but it's connected via a serial bus, a quad SPI bus, and that's simply not fast enough to do what we want. It can't even meet reading and writing a frame once at 60 FPS. And in practice, you will probably need a bit more for overhead and when you're drawing triangles on top of each other. So I'll draw things a little bit differently. What I'll do is I'll divide the screen into little vertical strips that are 4 pixels wide and 240 pixels tall. Why did I do tall strips instead of wide strips? Well, 240 just fits into 256, and 320 would fit awkwardly in 512. So that's why. And this size that fit neatly in that little block RAM that we had. So yeah, little strips. And this is also what I'll do for rendering. So far I've been talking about scan lines as you're used to on a television, but I'm scanning vertically. Calculations are the same, just flipped in order. And rendering we'll be doing strip by strip. And every time a strip is ready, we'll send it over to the LCD screen. And we'll do that, well, eventually you'll find that you'll have to draw multiple triangles, and you'll have to draw a triangle over multiple strips. So we need some way to remember the triangles that we're drawing, and we need some way to remember where we were, how far we are progressing over our triangle. And this will continue. So we have a slightly different architecture now. Instead of a full frame buffer, which we can't fit anywhere, we've got column buffers. We've got 2 of them, one to draw to and one to display. And we have a big FIFO for our triangles. And these will contain the full state of the triangle, including all of the counters that we've been doing as we're moving along the edges. And the SPI controller will now add new triangles to the FIFO. The calc line will take one of those triangles, do things for it as far as it can get within that little column, and then write back the updated state. So it will continuously fill up, get processed, and once a triangle is done, it has the full width, we're all done, it's removed from this FIFO. All right. Another thing we might want to do is draw triangles on top of each other. And for that, we can use a thing called a Z buffer. So instead of writing the color of the triangles, we will be writing the depth of the triangles. So we can draw on top of each other, but if we find that, okay, the triangle that we're drawing right now is actually behind the other triangles that has already been written, we won't write them actually to the output. It's commonly used, and fortunately for us, because we only render little strips, our Z buffer only needs to be the size of this little strip. Right, so new architecture, we've added a Z buffer, and we'll check whenever we are drawing a pixel, we'll check is our depth of a new pixel, is it in front of what we've already written before? And of course, once we've written something, we also need to update the Z buffer. All right, we want more, we want better graphics, we want textures. So what are textures? Textures are pixels, pixel data, images that we are mapping to a triangle somehow. So we know the coordinates of what we want to draw, and we're essentially mapping that to where we are drawing our triangle. And to do that, it's pretty straightforward. Instead of drawing colors, we are drawing coordinates. And then we are using those coordinates to look up in a little memory where the image data is. Doing it this way has some issues. This is what's called affine texture mapping. It's simple and straightforward, but it's not perspective correct. You can do perspective correct drawing. It involves more divisions, so we're not going to do that. Besides, if it's good enough for the PlayStation, it's good enough for us. Right, updated architecture. We now have a new unit that I call the shader. It doesn't shade a lot, but it does draw the textures. It will look up, based on the coordinates that it's getting, data from the texture memory. And this texture memory, of course, needs to be filled in from the ESP32 via the SPI controller. All right, so what have we got so far? We can draw pretty triangles with lovely gradients. We can draw triangles on top of each other. And we can draw them with little pictures. And we can do that all without using dividers. So that was the most important thing. Yeah, what's the end result of that? A very, very full FPGA. Like 94% full. But we got it. We got there. It does things. It makes pretty pictures. Then I will have some demos. I've made a port of a very famous demo, ST-NIC 2000 by Oxygen. What it does, it has a list of triangle colors and positions, all pre-calculated, and I just stream it to my FPGA and see the picture that I get. It runs quite well. Now, this is not entirely fair, of course. This demo was originally designed for an old home computer. There have been ports to 8-bit computers, so we should be fine with a really big ESP32. But still, I like that it draws it, and it was an easy thing to port to. And it looks impressive. I hope you agree. Thank you. One more demo, one that I did write myself and didn't just steal from someone. A little monkey, Suzanne. Real-time lighting, smooth gradients, and a big old texture in the background. So it can do some things. All right. Yeah, that is about it with the demos. Yeah, I'd like to thank the Badge team for building a great badge. If you missed MCH, I've been informed there are still MCH badges available. If you contact the Badge team via their Discord, they could be willing to sell them to you. All right. Yeah, thanks everyone for listening. This is my homepage. I also have the Discord link on there. I've got a link to the demo on the hatchery if you have an MCH badge, so you can play with it yourself. And, well, soon I'll upload the source code for you to play around with as well. That's it. Thanks, everyone. Are there any questions?
Over there.
Please.
I did see some shading on the last demo. Is this correct, or is this a feature?
Yeah, so it's not part of the FPGA. The FPGA itself doesn't do that. It just gets the corners of the triangle and whatever color it needs to be. So that's part of what the ESP32 is doing. It's crunching quite a lot, but that's Fortunately, it's not the bottleneck. The bottleneck is the SPI connection between the ESP32 and the FPGA. So we can do a lot. I think the last demo was running at around 30 hertz. The FPGA itself, if you're asking about that, it's running at a clock speed of 36 megahertz, which is as fast as I was able to push the Lattice ICE component. Yeah, so there's always a trade-off that you can do, and I needed to toggle in the Lattice Radiant software between area and speed, and sometimes with speed I got less area, and sometimes with area I got faster. But yeah, I play around with it, and then eventually it fit, and then I was happy. Right. Yeah. It is very possible. I didn't use that. I got started with the Radiant and I stuck with it. But the Badge team, if you look at their website, they've got a link for the MCH2022 Badge with lots of tools that you can use, open source tools, and I'm told they work really well. Right, good question.
Since it's an ICE40 FPGA, can you clarify which toolchain you used? Is it a proprietary toolchain from Lattice, or is it the open source YOSIS?
I used the proprietary toolchain from Lattice.
Do you expect any success in synthesizing using the open source, or?
I think so. I don't foresee any issues. For the memories, I mainly use the PMI primitives, and these should be directly compatible with YOSIS as well. So I didn't use the click wizards that much in Lattice, so it should be pretty easy to port. Yeah. Right. Yeah.
Okay.
If you have any more questions afterwards, I will be in the Brabant village, the Brabant embassy. So please come by. Also come by for a schrobbelaar if you want, a little drink. So yeah, hope to see you there then.
Okay, great. Give an applause.